Hello, welcome to Lesson 11 of CE 3372, Water Systems Design. This lesson begins our adventure, so to speak, into open channel flow components of water system design. In particular, the design of storm sewer systems and drainage channels and the like, as well as the design of wastewater collection systems, which are, for all practical purposes, quite similar to storm drain design systems, except we don't flow wastewater in open channels, at least not where the public can get to it. So lesson 11, going through the PowerPoint slides, is open channel flow, in particular normal flow. Now the kinds of open channel flow that you were introduced to in your fluid mechanics class would be normal or uniform flow. That's the discussion today. Rapidly varied flow, so that was flow that changed its behavior over a relatively short distance. The classic example of that is flow going from supercritical to subcritical in transitioning through a hydraulic phenomenon known as a hydraulic jump, and you've got to create that in the fluid mechanics lab, no doubt, and you've seen them in your day-to-day lives, whether you know it or not. An open conduit is simply a conduit whose upper boundary of flow is the liquid surface. Examples of open conduits are canals, streams, bayous, rivers, and such things. Storm sewers and sanitary sewers are special cases of open channels. Most of the time they are operated as open channels, but occasionally they're operated as pressurized pipes, either on purpose or by accident. If it's by accident, that's usually problematic. The relevant hydraulic principles are the balance of friction, gravitational, and pressure forces. For a particular discharge, quantity capital Q, the flow at any section can be described by the flow depth, the cross-sectional flow area, the elevation, and the mean section velocity. The flow depth, depth area, depth perimeter, and depth top width relationships are not unique, so they can exist at least in two states, and so the knowledge of the flow type, whether it is subcritical, critical, or supercritical, is relevant. Uniform flow, or normal flow, is flow in a channel where the flow depth does not vary along the channel. In uniform flow, the slope of the water surface would be the same as the slope of the bottom of the channel, and actually, in fact, the energy slope would also be the same. We'll see that in the next lesson when we look at the gradually varied flow derivation. So here's a diagram, a elevation view sketch of some open channel, and the water surface is right there where the red line is appearing. And we're looking at two sections. Section 1, which I've drawn as upstream, section 2 is downstream, and I know that's the case because I've got my flow arrow right there. So at section 1, the total energy we're going to discover, or going to declare, is equal to the elevation of the bottom of the channel above some datum, plus the flow depth, y1 in this case, plus the velocity head at that location, v1 squared over 2g. At section 2, its total head will be the elevation to the bottom, plus the flow depth, plus the velocity. The hydraulic energy at a section is the sum of these three components: elevation head, pressure head, and velocity head. I've drawn them here in green for elevation, blue for the pressure, which is the flow depth, and red for the velocity head component. The distance between these two sections is drawn here as delta x. We'll see that again when we do the gradually varied flow. And if we were to take section 2 as a reference point, the change in elevation between section 1 and section 2 is going to have a magnitude equal to the bottom slope S sub 0 multiplied by the station distance delta x. The water surface is the hydraulic grade line. So that's the height that water would rise to in a piezometer if there were a piezometer, but the entire open channel is a piezometer. Therefore, the water surface and the hydraulic grade line are coincident features. The locus of points of total hydraulic energy, or total head, from station to station to station, if we keep track of where that is, the line that describes that is called the energy grade line. And it bears the same relationship as the energy grade line in a pipeline system. The slope of the energy grade line is this term, S sub f, and that's goes by a variety of names. Friction slope is kind of an old-timey name, but still used in practice. The bottom grade line, or the flow line, or the topographic line, is shown here in green, and its slope is sub 0. Now, if there were no head losses in the system, zero friction, then Bernoulli's principle would tell us that the total head at any point in the system is the same, and that would be this dashed red line across the top. Instead of the dashed line, we're down here at the energy grade line locus, and the distance between those two, the horizontal dashed line and the energy grade line, is the head loss moving from location 1 to location 2, and the head loss is equal to the friction slope multiplied by the distance between the two stations, delta x. As a funny aside, head loss is what happens if you're bad at governance. And here is, during the French Revolution, it turned out that the leaders weren't very useful, and so the popular people introduced a head loss equation to change their government. Uniform flow is the case where the two flow depths, y1 and y2, in the previous diagram are the same. In such a situation, the friction slope would be the same as the bottom slope, S sub 0. And in fact, this equality is the definition of uniform flow. Gradually varied flow, on the other hand, means that the change in flow depth moving upstream or downstream is non-zero, means that y1 and y2 are not necessarily the same, and it's gradual in terms of distance. In other words, a waterfall is not a gradually varied flow situation. But the long run-up to the edge of a waterfall very well could be a gradually varied flow situation. In gradually varied flow, the two flow depths, y1 and y2, are not necessarily equal. Rapidly varied flow, which we won't mess with much in this class, means that the change in flow depth occurs over a relatively short distance. Relatively short would be a couple of characteristic diameters. So if you think the channel's 10 feet wide, the relatively short distance would be 20 to 40, maybe up to 100 feet, versus gradually varied flow, which in a 10-foot wide channel might take hundreds and hundreds of feet to see a visible change. Flow coming out of sluice gates or in hydraulic jumps or through energy dissipators is usually rapidly varied. Now we can take the sluice gate flow and treat it as gradually varied until it gets close to where it's going to hydraulic jump, and then it would be rapidly varied, and then we can continue onward with gradually varied flow. So open channel design, the concepts are pretty simple. We want to estimate the required system capacity, Q. Usually this estimate will involve some hydrology, or in the case of sanitary sewers, the number of anticipated service connections. The second step would be to use the uniform flow assumption to make an initial conduit sizing with adequate freeboard selected slopes to achieve design velocities. Next, we would want to evaluate that design using a hydraulic model, especially in the case where backwater effects are anticipated or likely. If the hydraulic model is satisfactory, then the design is likely to be hydraulically adequate. If not, we'd adjust the design, either by changing slopes or diameters or using vertical offsets at the junction boxes to achieve the desired velocities and capacity. Once that's done, we want to be sure that the other non-negotiable constraints are satisfied, things like alignments, right-of-way, setback distances from other systems, and so forth. And we iterate between 3 and 4 until we have some workable alternatives, estimate the cost, present to the client. So those 5 steps sound really simple, but they often involve a fair amount of effort. Conduit sizing itself requires knowledge of the depth area, the depth perimeter, and depth top-width relationships at a cross-section. Regardless of the section type, whether it's circular, rectangular, trapezoidal, or irregular, natural channel, the relationships are all based on the same common theme. The important relationships are depth versus area, depth versus perimeter, depth versus top width. So here is a diagram of some arbitrary cross-section, and depth is measured from hopefully the lowest point in the channel of the cross-section to where the water surface is. So depth is the distance to the water surface. Ignore this differential area above it for the time being. The area is equal to this differential area integrated from y equals 0 up to whatever the depth is. So this integral says the area as a function of y is the integral from tau equals 0 to tau equals y of top width of tau d tau, where we have to know the top width relationship. For things like rectangles, trapezoids, and circles, that's pretty straightforward. For irregular channels, we often have to perform numerical integration. Generally, professional design software handles that numerical integration on our behalf, but occasionally it's useful to know that's what's happening, especially to check the work of the computer program on the off chance that there's been a data entry error. The depth-weighted perimeter relationship is the length of the red line in this diagram. And that weighted perimeter is simply the liquid solid contact area, or liquid solid contact interface. And the length of that, this red line, is called the weighted perimeter. And it's clearly a function of depth, because if it gets deeper, you get a little bit more length over here and a little bit more length over here. So let's look at some simple geometries and proceed forward. We'll start with the rectangular conduit. Examples of actual rectangular conduits are box culverts flowing with a free surface. Rectangular channels are quite common in many urban drainage systems. Such channels will have to be concrete lined because maintenance of the soil line rectangular channel would be nearly impossible. The angle of repose of the soil would be unsatisfactory and it would fall into the channel. But there are rectangular channels in cities that are pretty substantial in size, big enough to drive all-terrain vehicles through, motorcycles and so forth. The preferred location of terminators when they're being chased and such. So here's our rectangular conduit. The bottom width is B, the top width is T, and Y is the depth. Now, because it's rectangular, the top width and the bottom width, if there's water in it, are going to be the same numerical value. So the top width as a function of y is equal to the constant b. The area as a function of y is equal to the constant b multiplied by the flow depth y. And the wetted perimeter is equal to the length along the left, which is y units long, plus b units long, plus y units long. So b plus 2y. The hydraulic radius is a concept that's used so the hydraulic equations can be applied regardless of geometry to one another. For rectangular geometry, the hydraulic radius can be expressed as this formula here. b times y over b plus 2y. Generally, we don't go to the trouble to express them in this way, and we often just calculate the area divided by the wetted perimeter and declare that the hydraulic radius. If the channel is really wide, so if B is very large relative to Y, we can simplify this version. If B is big relative to Y, then in the denominator, the 2Y isn't very much of the denominator, and mostly it's made up by B. If that's the case, then those B's would cancel, and so for a wide channel, Mississippi River kind of wide, the hydraulic radius is approximately equal to the flow depth. If it's not wide, we won't make this observation. Trapezoidal channel is also a relatively common geometry. Triangular channels and rectangular channels are special cases of trapezoidal conduits, so if you happen to have a tool that could do trapezoids, you by default can also do triangles and rectangles. Engineered or improved natural channels are pretty well approximated by trapezoidal channels, and the geometry is relatively important in drainage engineering. A lot of the engineered channels that you see in the movies, the other preferred geometry of terminators and people chasing them on motorcycles is trapezoidal channels. The side slope is generally expressed as the horizontal to vertical ratio. So if the horizontal ratio is m units and the vertical ratio is 1, the side slope would be expressed as m. The flow depth has the same meaning as before. It's the depth above the bottom of the channel. The bottom width is the width at the bottom of the channel, and the top width is the width at the free surface channel interface. With those definitions, and in this case this is for a trapezoidal channel where the left side slope and right side slope are the same, we have the area is equal to y times b plus my. The top width is b plus 2my. The wetted perimeter is b plus 2y multiplied by the square root of 1 plus m squared. And finally, the hydraulic radius is the ratio of the area and wetted perimeter. Y times b plus my divided by b plus 2y root 1 plus m squared. Again, like I said a few minutes ago, we wouldn't actually attempt to simplify that. There's no real advantage to doing that. Just calculate the area, calculate the wetted perimeter, take the ratio, that's the hydraulic radius. So for trapezoidal channels, they occur often enough that it's worth having some tools available. So one that's available in the class website is a trapezoidal channel hydraulic element calculator. Over here, it actually shows the equations that are used. You enter the values, choose the submit button, and it will return the various elements of the channel. So let's go ahead and escape from the presentation briefly, and we'll go to the toolkit and verify that it's still producing the same values. Toolkit has been escaped. Go to the toolbox, Open channel hydraulics, trapezoidal, hydraulic characteristics. Well, currently it doesn't seem to be able to acquire the graphics. Oh, it just takes time. I'm making this video while downloading and compiling a fairly extensive computer program, so everything's slower. Okay, so the bottom width is 5 feet. The side slope is 6:1. This one has left and right side slope, so we'll enter the same values for that. And our flow depth is 3 feet, and when we press the submit button, it went ahead and made the calculations, and it reports back a flow area of 69 square feet, a perimeter of 26 feet, and a hydraulic radius of 2.6 feet. If we cared, tell us the flow width is 41 feet. So if we were trying to fit this into a 40-foot right of way, we would have a problem because we'd already be flowing over the sides. If we want to do a rectangular conduit, we simply use the same tool, but we give it the set the side slopes to 0. And we get flow area of 15 square feet, perimeter of 11, hydraulic radius of 1.36. Next one will be the circular conduit. The circular conduit is quite common in engineered systems, and they're going to be treated using the tools here. So here we have a pipe with diameter D. Here's a free surface in it at a depth Y from the bottom. The top width is shown as this solid line across here. And the centroid of the circle is located where the cursor is, and if we move out to the edge, that distance is always a radius. So the angle formed between the vertical bisector and this radius that goes from the center to the water solid contact point is called alpha, and we choose alpha because it looks like a fish, and this is full of water, and fishes swim in water. Unless you could use beta, I guess that's a beta fish. Anyway, I've chosen alpha as the angle between the vertical bisector and the top width contact. Other authors choose the entire angle between the two rays. So you'll need to be very careful when you're using the resulting equations that we're about to see in a second to be sure that you know whether it's the half angle formula, which I'm using, or the complete angle formula, which other authors use. And they're both correct, but if you misinterpret the two, you'll be solving an entirely different problem, not the one you want. Okay, so here is the result of the trigonometric analysis, and rather than go through the derivation, I'll just present the results. But any one of you in the class by this point in your engineering education career would have no trouble deriving these from your trigonometric relationships that you learned back in trigonometry. So alpha of the circle as a function of depth y is equal to the arc cosine of the quantity 1 minus 2y divided by diameter. Once we have defined alpha as a function of depth, the remaining terms can be represented as functions of alpha. And since alpha is a function of depth, they're also a function of depth. So the area of the circular conduit as a function of y is the diameter squared over 4 multiplied by the quantity alpha minus sine alpha cosine alpha. It's important to remember that alpha has to be expressed in radians. Can't use degrees or gradients and get the correct answer. So if you're doing it in degrees, you'll need to convert it into radians. There are 2 pi radians in 360 degrees, and there are 2 pi radians in 400 gradians. Yeah, I think that's right. The top width is a function of y is the diameter times the sine of alpha, where alpha is in radians, and the wetted perimeter is a function of y is the diameter times alpha, where alpha is in radians. The hydraulic radius, therefore, is the ratio of the area and the wetted perimeter, and that's d squared over 4 quantity alpha minus sine alpha cosine alpha divided by d times alpha. So again, online tools are available, and if we supply depth and diameter, it can return the information regarding a particular hydraulic element. So we'll go back to our toolbox, go back to open channel, circular conduit. Oh, looks like it was being funny here. It says SI units. It actually doesn't matter. This is in feet and feet, but it could be in meters and meters, and it will do the correct arithmetic. It'll just report the wrong units. Okay, so we'll put in 6 foot diameter, 5 feet of flow depth, and it tells us that our wetted perimeter is 13.8 feet, flow area is 25.17 feet, hydraulic radius is 1.82 feet, 1.83 depending on how you round it. Find something interesting if we go to half diameter. So pipes that are half full, the sweep angle is going to be the sweep angle is going to be pi over 2, which makes sense. Top width is 6 feet, so top width is equal to the diameter. Wetted perimeter is half the total wetted perimeter. So the half full and full circle are actually quite easy to do using the definitions of circular areas that you're accustomed to. But anything else is a little bit more complicated. So sometimes it's useful to have depth area discograms or diagrams if you can spell correctly. The designer should sketch their own definition sketches before using the equations to validate that the equations produce the desired results. So if you use my tools, you've seen the sketches now. They are important to understand, particularly implement. There's other geometries that are common, and these depth area tables are constructed on an as-needed basis. So there's horseshoe, there's egg, and there's a few other common shapes. There's actually a rectangular with a U-shaped bottom and a bench, which are common sewers of old cities, Amsterdam, New York, and so forth, have these benches in them. That's so that you can walk down in the sewer and fish out sewer fish or go do maintenance. And they're also popular places to film creepy movies. The circular conduit is obviously a nuisance to relate the hydraulic elements because of the implicit nature of the expressions, especially when the diameter is unknown. So the two reasonable approaches are to build a calculator. The online tool is one such calculator. We'll look at some spreadsheet calculators in a second. Or use an ID10T computation sheet and a hand calculator. Or use a dimensionless chart that relates full pipe behavior, where the relationships are simple to compute, to partial full behavior. So calculators are ultimately for doing depth discharge relationships, usually using Manning's equation. And here's Manning's equation in U.S. customary units, so 1.49 over NA r to the 2/3 s to the 1/2 power. In practice, that slope is supposed to be the friction slope. Excuse me, in theory, that slope is supposed to be the friction slope. In practice, we often use the bottom slope because it's the only one we have, and it's the only one we can reasonably specify. So this equation presented here in this presentation slide is the same as Manning's equation on page 161 of the NCEES supplied reference. It's an adaptation of equations 342 and 3288 in Chin. The drainage engineer in the U.S. should memorize this equation. If you do it in SI units, that 1.49 is replaced with a 1. So it's really not that hard to convert between the two unit systems. So what such a calculator might look like. So you might make a spreadsheet where we supply values of Manning's N, supply a value for depth, a diameter, and slope, perform the necessary intermediate computations to produce discharge velocity and, discharge and velocity. If we display it as spreadsheet formulas, it looks like this, and we also can have an online calculator for the Manning's equation part. Now, using the Manning's equation calculator, we actually have to have two instantiations of online tools, one to get the hydraulic elements and the second to do the Manning's equation calculation. That's by intent. It wouldn't be all that hard to build it into a single tool, but this slows things down and makes us think. So let's go ahead and take a look at that. See if I can do File, New Tab. There's my Manning's calculator. It has internal references to Manning's N values. And it has the equations explained here. Okay, so let's go to the example that's in the PowerPoint and replicate it. That was a 6 and 5 most likely. Okay, so there is that information, and now we want to populate the slope area. So we need to have a value for Manning's N. In the presentation, looks like I used 0.013. I looked that up in one of these tables. So you would select that value based on the material properties of the conduit you're interested in. We then provide the flow area. We use all those digits because they got to be significant. We then provide the, I think it uses wetted perimeter. And finally, dimensionless slope, which was 0.005. And we get our discharge, which it looks like I solved a completely different problem. Yeah, well, I solved a different problem, but that's how to implement the tools. If we want to solve the problem that was there, the actual one that's in the thing, this I believe is 69 feet, and this is 26.63. And now we have the identical solution. Okay, so that's a tool to help you do Manning's calculations relatively quickly. And this is not hard to do on a hand calculator, but it's pretty convenient to be able to just log into a website and access the calculations directly. Okay, a second approach is to make a worksheet. This is so that you can do it when all you have is a hand calculator, and you don't have stuff committed to memory, and just follow the instructions. So here's what the sheet looks like. You'd enter a value for Manning's N, flow depth, conduit diameter, conduit slope, determine the flow depth to diameter ratio. We compute the cosine of alpha according to the formula, compute the inverse of the result on line 6 in radians. Basically, it goes through all the calculations that a computer program does in an instant. So this is a very slow way to accomplish it, but it documents every step of the operation. And switching to SI, the only change is right here at the end. Okay, another approach are dimensionless diagrams. If we use the same principles as the circular flow calculator, a dimensionless depth discharge diagram table can be constructed. Essentially uses the same input information of diameter, material properties, and slope. The table then divides the depth into specific ratios of the diameter, computes the discharge for each ratio. In the forward computation step, there's absolutely no advantage. If one has the tabulation or the dimensionless chart, then reverse lookup is greatly simplified. Okay, that came out buggered. Doing it in the forward direction, there's no advantage. Where this comes useful is when we have to go the reverse direction, where we have desired flows, desired slopes, and we want to figure out what size pipe to use. So one way to produce the dimensions diagrams is shown here. So here you have Manning's N, diameter, dimensionless slope, flow depth in feet as a fraction of pipe diameter, flow depth ratio, then you compute the various angles, and we finally get the discharge in cubic feet per second. So if we change diameters, change slopes, change Manning's N, all these numbers will change. But all it's doing is a sequence of Manning's N calculations for different partially full pipe depths all the way up to full depth. Now you notice something interesting is that the pipe flowing full has a value in this case of 0.97, but the values of the pipe almost full are actually slightly higher, and that's not unusual. That's how open channel hydraulic element charts are constructed. It's an interesting phenomenon, which gives us a little bit of factor of safety inherent in any design. If we design for full pipe flow, we have a little bit sneaky extra capacity right in here, assuming the pipe is coming from low fill depth towards the full depth. Here's what the plot looks like of those calculations. And how would we use that chart? So the way you would use a chart like that is first you would determine the full pipe discharge, which is 1.49 over n pi d squared over 4, diameter over 4 to the 2/3 power, slope to the 1/2 power. That's pretty easy to remember. Then you would determine the flow depth ratio of interest. Let's suppose we're interested in 3/4 full. The ratio is 0.75. We go to the chart and we want to locate the discharge fraction for the depth fraction on the chart. So for example, for 0.75% full, the Q to Q full ratio is 0.91. So for 0.75 full, come over here, and we're at 0.91. Then we multiply the discharge fraction by that full pipe discharge fraction to recover the discharge for a particular depth. Thus, the Q at 75% full is 0.911 Q full. If you don't want to build your own chart, the NCEES supplied reference has a hydraulic element chart for circular sewers, and there's lots of other sources of this particular chart. The one often of interest is this red line, where Manning's N is presumed to be constant regardless of the fill depth. So the value of these charts comes from doing reverse lookups. So where you have a desired fill depth and a supplied discharge to look up backwards to find the required diameter. There are other dimensionless charts for different geometries. This is an example from FHWA HEC 22 manual for a trapezoidal channel. I've extended the chart down here for some other reasons a while ago, but here is the procedure. You have to specify the channel width and the side slope, the longitudinal slope, material properties, and discharge. Then you locate the value of bottom slope on the first vertical scale. Compute the quantity discharge times Manning N. That's on the second vertical scale. Once you locate those two, you draw a line to the turning line. Locate the value B on the fourth vertical scale, so that width, and then you would extend the line from the turning point through the value of B until you hit this curvy looking thing, and that's the D over B ratio chart. At the intersection of the side slope scale and this line, you would draw a horizontal. So here's the various side slopes. So let's say we had a side slope of 6, which is pretty common. And the follows it. Then read the depth to width ratio directly from this right hand side. So this line goes through here, and then you intersect it at the desired side slope, and then you run horizontally across. Okay, so next time we're going to look at gradually varied flow, and we'll demonstrate that normal flow happens to be a special case of gradually varied flow. And before we quit, we also have we also have a set of spreadsheets that are available. Hopefully it will maintain my connection. Yay! Cool. It doesn't happen very often. So in lesson 11, there's a link to spreadsheets. So there's a discharge depth circular table spreadsheet. Go ahead and open and run that. Lo and behold, the pipe diameter 5. The chart doesn't change, but the numbers change. I'm pretty sure these are the same. And these are small calculators for doing the calculations, just like the online tool. Perhaps the advantage here is that the formulas are embedded in the spreadsheet, and so you can understand the calculations that are being made. Plus, it's easy to add additional components to the existing spreadsheet. The ID10T worksheets, on the off chance you actually need to use them, are here. And that concludes this video for lesson 11. Thanks for watching, and have a good day.